In the previous sections, we worked with text. However, we treated text as just a bunch of characters that have no meaning. For example, we search for a particular text pattern in a piece of text. For example, searching for the word was. When you do that search using regular expressions, which was the technique we used previously, you are searching for the exact word, WAS. However, that might not be enough in some application areas, such as artificial intelligence. In those scenarios, you might want to do more intelligent searches. So, to follow this example, in this case, you'd also want to return a match if the text does not contain the words was, but another form of that word. For example, is. So those two verbs come from the same root, the verb be. So in artificial intelligence applications, such as chatbots, for example, you'd want to consider those words as similar. And this is where natural language processing comes in. It is a technique that takes into consideration the meaning of the words and doesn't just look at the words as a sequence of characters. So in this section, you learn how to perform natural language processing in Python, and you learn all the top libraries that are needed to process natural language. And after this section, you'll apply the knowledge to build a chat bot that answers questions by getting information from Wikipedia articles. So it's quite an exciting app and very interesting videos. So thank you, and I'll talk to you in the next one. Get ready for this. Hi, welcome back. In the previous video, I gave you some clue on what you'll be doing in this section. And we talked about comparing words, which is one of the main activities you can do in natural language processing. You compare if this text is that text, and you try to find out if they mean the same thing. So this is what I'll teach you in this lecture, how to do that. So let's take an example. Let's say we have these two words. They have the same meaning. They derive from the word be, the verb be. So how can we find out that, how can we tell that these are the same verb? Of course, if you just do x is equal to y, you get false. So how can we get true for this? This is where natural language processing comes in, and we do natural language processing using a few libraries. The main one is called NLTK. NLTK, which stands for Natural Language Toolkit. It's a third-party library which you need to install, but on DeepNote you don't have to do that because it's already installed. I'm using DeepNote as a notebook. Now, NLTK provides a lemmatization function, which allows you to find out the root of a word. So in this case, we want to find out the root of was and the root of is, which is be. So the root of was is be, the root of is be, and then we want to compare if the root of that word is the same with the root of that word. So be is the same with b, therefore we will get true. So the idea is to find the root of the word. You do that by importing from NLTK.stem, you import the word net Lemmatizer class. This is a class, so you want to create an instance of that class first. So I'm going to execute this. Successful. Create a new code cell with Ctrl J or Command J, and I'm going to call this variable Lemmatizer, which is equal to word net Lemmatizer with parentheses. So now we have a Lemmatizer instance which we can use in this other cell to get the root of a verb. The root is also known as the lemma of the word. So I'm going to have a variable lemma is equal to lemmatizer, the object instance that will help us through the lemmatize method to get the lemma of the words. So the first argument is the words, and in this case it would be x, so the words was, x contains that string, so x. And the second argument, as you see here, so the first was the words, the second is the part of speech tag, also known as the pos. So this is where you define what type of word this is. So you need to say that this is a verb. Now this can also be automatic, so we can let Python understand the root of the word, but we'll do that later. So let's take it step by step for now. Let's tell Python that this is a verb, so the lemmatize method knows how to get the lemma of that word. So V for verbs, A for adjectives, R for adverbs, and S for satellite adjectives. And N, of course, is the default one. If you don't want to place an argument here, then it will be a noun. So a verb is this in our case, and let's call lemma here to see the version of was. Now we get this lookup error the first time when you execute this, and that is because you first need to download the word net dictionary, which contains all the English words, because you're trying to get the lemma of this word, but you need a database to get that information, right? And this database should be an English dictionary for this method to look up the lemma of the word. So before you do that, you want to create a code cell and do NLTK download wordnet. Execute that. We need to import NLTK. So execute again. Yeah. So it downloaded and unzipped this wordnet file. So let's execute again. And this is the output. So B is the lemma of that word. Similarly, we can get the lemma of the other words. So let's call this lemma 1. And the other word would be lemma 2 is equal to lemmatizer. Lemmatizer, the same instance that we got here, dot lemmatize. This time is Y, that word. So is, and this is also a verb. Lemma 2 is again B. So then we can compare lemma 1 is equal to lemma 2, but let me execute the lemma 1 variable first, because we renamed it. Lemma 2, execute. There we go. So now we are saying that these two words are the same. And that is how you do that. So let me put all the code in one single cell to make it look better. This, maybe it's better to have it on top here, or even in a separate cell, because this should be only executed once. You only have to download that once, that dictionary. And then we created the lemma of the first word, and then we created the lemma of the second word. And then we compared if lemma 1 is equal to lemma 2. And we got true. So that's how you compare words by taking the meaning of the words into consideration. This, of course, has a problem, because if you try to get another word such as vegetable and compare it with vegetable, so the plural form and the singular form of these two words, you will get false, because you see that lemma 1 is vegetables. So when you have verb as the second argument, this lemmatize function will not know how to get the lemma of that word. But if you say noun, then you get vegetable. So you say that this is a noun, and then the method knows how to get the singular form of that noun. So that is a drawback that doesn't let you automatically get the lemma of all the words without knowing what they are, but it has a simple fix. We can simply get the information if this is a noun or a verb, and then provide that information dynamically in here so that we don't have to know beforehand if this is a verb or noun, an adjective or an adverb. So we'll do that in the next video. See you there. Previously you learned how to lemmatize words using the lemmatize method. In this video you learn how to lemmatize complete sentences. So which means that you will find the lemma of each word in a sentence and then be able to compare two sentences if they are the same. So the lemma is the basic form of a word, as you learned in the previous video. Now, of course, so far we have simply done a simple comparison such as if this lemma is equal to that lemma, but later on we will do more complex similarity comparisons, which will give us a certain value, a degree of similarity between two sentences, because sentences cannot always be exactly the same, but they could be similar to a certain degree, which tells us if this text is related to that text or not. But before we do the comparisons, of course we have to lemmatize sentences in order to get better results. Of course, you can also compare two sentences using the similarity algorithms that I'll teach you in the next videos without lemmatizing, but with lemmatization you get more accurate results. So let's focus on lemmatization of sentences in this video. Now you cannot simply use that code with a sentence. Let's say vegetables are types of plants. This will not work. Let me also download the WordNet dictionary first before I do the lemmatization. Port NLTK, so you have to do that anytime you restart the notebook. At least when using deep notes. If you're using a local Jupyter notebook, then that shouldn't be the case. You don't have to run that every time. So execute again. And let's check what lemma 1 is. So vegetables are types of plants. Nothing happened because this method is designed to get single words as inputs, not sentences. So we have to do something before we provide the words here. We have to first divide the sentence into words, also known as tokens, and this process is known as tokenization. So let me convert this using Shift Command or Control M. I'll convert it into a text cell. So tokenizing sentences. To tokenize sentences, you can use the NLTK.wordTokenize method. This expects a string as input, so that would be this sentence. So I'm going to save that sentence here in a variable. Sentence is equal to that. Let me remove that part. And I have to execute this cell now to record this variable in the namespace. And this will not work for now because it's empty, so remove that. Tokenizing sentences, these will get a sentence as an input. If you want to save the result of this word tokenize method in a variable, then let's do sentence tokens. So we're getting the tokens of the sentence. And let me print them out here. Now, for this, we need to download the Punkt dictionary. So let's execute that as well. Execute. Download successful. And this is the result. So it's a Python list made of different items. Each item is a string and it contains the parts of the sentence. So you could also do this splitting using the Python string method called split, but this method is more appropriate because it also takes into account different punctuations of language, of the English language in this case. So it will be more accurate in giving you a set of words for a sentence. However, you should use the lower version of the sentence because that will give you all these tokens in lowercase, so the lowercase version. And this is needed because now we will pass these inputs, these words, into the lemmatize method, and the lemmatize method works on lowercase words only. So let's lemmatize each of these words. For that, I think we need a for loop. So we need to iterate over each token. So for token in sentence tokens, and then point to the lemmatizer instance in here and call the lemmatize method, which expects two arguments. The first one is the word, so the token in this case, that, and then that in the next iteration, and so on. So the token and the tag, which could be a verb, could be a noun. The problem is we don't know whether each token will be a noun or a verb or an adjective. So let's try first with n as the second argument and just print lemma just to see what's going on here. So vegetable was successfully lemmatized. You see, from vegetables we got vegetable, but R is not lemmatized. The lemma of R should be B, but it's not B here. So if we change to V, then we get B for the verb, but not the lemma, the correct lemma for vegetables. So we need to provide this in a dynamic fashion. For that, we need, in this upper cell here, I'm going to create tags, pause tags, for each of these tokens. Pause means part of speech. So part of speech tags. You'll see what these are. You need to use NLTK dot pause tag, that method, which expects a list. So sentence tokens, in this case, that one, that's lists. And then I'm just going to print this out, and this is the output. You might get an error saying that you need to execute NLTK, download something, a dataset, so just execute that and then execute this code again if you got that error instead of this list. So in my case, I had downloaded before, so no errors. This is the output. So this is a list of tuples. Each tuple has two items. The first item is the token of the input list. So vegetables are types of plants and the period. And the second item is the tag. Now we're interested about the first letter of the tag. And for the first item is N, which means it's a noun. Vegetables is a noun. R is a verb. Types is a noun. Of is a preposition. EI is the code for the prepositions. Plants is a noun also. If we had adjectives here, we would get A for adjectives and R for adverbs. Now let's make use of that list of tuples in our for loop here to extract that first letter from each tuple. For that, we need to iterate over both the sentence tokens list and also the post tags list. So they have the same number of items. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They always will have the same number of items because we're talking about the same sentence tokens. So to iterate over two sequences at the same time, you need to wrap them into parentheses and use zip. And then you need two variables. So for token, pause tag in zip sentence tokens pause tags, and then we do the rest. So in the first iteration, token will be equal to vegetables, and pause tag will be equal to that tuple. So then we can put vegetables here, and then in here, instead of that, we put the dynamic pause tag. But be careful here, because pause tag is the tuple, the entire tuple. What we want is the second item of the tuple. So we say 1 there, the index 1, which gives us that string NNS, and then we want the first item of that string. So we only want the n. Therefore we say 0 here, and we want the n to be lowercase. So we say dot lower. That is equal to lowercase n in the first iteration. In the second iteration, it will be a lowercase v, and so on. And then we print the lemma. So I execute that, and I get this output. Vegetable, so vegetables was converted into vegetable, vegetables to vegetable, R to B, so far so good, types to type, and then of is not converted at all. We get this error, key error. And if you see the error, the entire error, you'll find out that the reason for this is of doesn't have a lemma. So this method here will not work for prepositions. Therefore, we need to make this more intelligent and check if pause tags, so let me copy that, if that in a list of n and v and a for adjectives and r for adverbs. So if the pause tags is one of those, because only these have lemmas, not I, for example, only in that case we want to find out the lemma and print out the lemma. Else we just print out the token as it is. If I execute that now, we will get this. So vegetable, B, type of plant, and the period. Of course, if you don't want these prepositions and the period, which I think you shouldn't include them in comparisons because they don't have any real meanings. So usually when you work with natural language processing, you want to work with verbs and nouns and adjectives and adverbs. So I would say that you can just leave out those and just work with the words that can be lemmatized. So vegetable, bee, type, plant. Now, of course, these are printed out here. So if you want to save them in a list, then you want to create here a list, such as sentence lemmas equal to an empty list. And then instead of printing that out, you can say sentence lemmas.append and append the lemma there. And then exit all the loops and call the sentence lemmas variable. Then you get the results in a sentence form. So we can then modify this code to compare two sentences, or even better, put it in a function. So let me create a function, define lemma me, let's say like that. This will get as input a sent variable, which is a sentence, and then we need to tokenize that sentence in that function. So I'll get that and copy it in here. So we get sent here, sentence tokens is equal to that. So this should be sent now. The function will get a sentence, one string as input. It will convert it into sentence tokens, and then I'll indent that under the function sentence lemmas for token post tag in zip sentence tokens. So that one, that local variable is here. We do that, sentence lemmas. I'll return that sentence lemmas and execute the function definition, and let's call the function lemma me. And what was, yeah, this sentence. Let's try that sentence. Execute, and we get the tokens of that sentence. If we try to change that or save that into a variable L1, right, L1 is that, and use the function again, L2, with another input string, lemma me is the name of the function, and this time let's say a vegetable is a type of plant. L2 here. It seems we didn't get the correct results because we have this variable here, which is also a global variable, so things are getting messed up in here. And this is the case sometimes with Jupyter notebooks. So I'm going to refresh this page. You can, if you're locally, you can restart your notebook. And then what I'll do is I'll just execute this function only. Of course, first import NLTK. So I'll execute only this so that I don't get that sentence tokens variable in the namespace. Then execute that. L1 is vegetable, B type plant. L2 is, oh, we got these results. A vegetable is type. So it seems it's not working because the post tags were created in here for this tokens. So we want to also get that post tags and put it under sentence tokens. So we create sentence tokens in here, and then we create, using those sentence tokens, we create post tags, and then use those post tags in here. So it didn't work because post tags was being used with a previous sentence since it was defined globally. So with this sentence, now it should work. But you need to execute the function again, and then execute that, and then execute that. Now we see that the tokens are the same. So we can compare these two variables if they are the same, of course, and we get true. So that is how we compare two sentences using natural language processing. Of course, this is an exact comparison, as I mentioned in the beginning of the video. This doesn't give us a percentage and a coefficient of similarity. For that, we're going to compare two sentences in the next video and get a coefficient of similarity. And then we can put a threshold. We can say if this coefficient is greater than this, then these sentences are the same, and so on. So I'll talk to you in the next video. Hi, welcome back. In this video, we will write an algorithm which gets a sentence, which usually is a question. For example, what are vegetables? And then the algorithm also has access to a variable which has text. And in that text, there are several sentences. So the algorithm should find the answer to that question in that input text. So this is a common case for chatbots, when you have a chatbot which answers questions. In the next videos, we will build a chatbot which answers Wikipedia questions about a certain topic, and the chatbot will read a Wikipedia article and give you the answer. So that chatbot is based on this algorithm that we will write in this video. So in this algorithm will get this question, and then it will return the sentence among these sentences, the sentence that is the most similar to this question. So what are vegetables? We expect to get vegetables are all plants from this algorithm. For this we will use NLTK, the library we have been using. So we will reuse some of the code of that NLTK library, the code that we wrote previously, and then we will use scikit-learn, which is a library that allows us to do this matching of the best sentence given another sentence. So let's first see what code we need from the NLTK library. We actually need this Lemma function in here, which, just to remind you, what this does is it gets one sentence as input and it tokenizes that sentence into words, so it generates a list of words. Each word is an item of that list, so one list here, and then for each item we find out the tags, which is the type of the word. So for each word we know what type of word that is a verb or a noun or etc. And then we convert each word into a lemma, so we find the lemma for each word. And if we get that function, for example, if we input this sentence into that function, we would get as output from that function a list which would look something like what be the lemma of R and vegetable, the lemma of vegetables. So that is the output of that function, this kind of list. So we need to get that and copy it in here. So we do have that function now. Then what else do we need? A scalearn dot feature extraction dot text import T, capital T, F, I, D, F vectorizer. That is a class which will do a statistical analysis which will find out the importance of a word in a corpus. A corpus is basically a piece of text. So this will help us build a matrix where we have the importance of each word, and that will help us to compare the similarity between sentences afterwards. You'll see how that works. So execute that, and then we need to create an instance of that class. Now, I said that this class is working on finding the importance of words. So therefore, this needs to have some sort of list as input, a list of words. But instead of inputting the list of words here, this class is designed to get as input a tokenizer. A tokenizer which tokenizes sentences, so it converts them into words, and we do have that function. So that is the Lemma function. So this function should get a sentence and should return a list object type made of words. That is what we do there. Execute that. If you see TV, there's nothing to see right now because this is just a representation of the class without any values yet. Now we need to do that finding of the word importance using another variable here, tf for this, and we need to use that object type and point to the fit transform method, which is an algorithm that will get the sentence tokens as input. Now, what is the sentence tokens? Well, this is a variable that we haven't defined yet, actually. So we need to define this, perhaps under the function here, in a new cell. So we need to calculate the sentence tokens. This will be NLTK.sendTokenize, and we get text as input. So we're working on this text in here, and if you see what we get from this, is a list of 3 items. Each item represents or is a sentence of that text. So originally vegetables were collected from the wild by hunter-gatherers. That is the first sentence. And then we have vegetables are all plants in here, and so on. We have 3 items in that list. If you got an error saying that you need to download some NLTK dataset, then just execute that code that is shown in the error to download that dataset. Then I can execute that. Since I have this variable now defined in here, I can go ahead and execute it. Now this asks me to download that, so I'm going to create a code cell in here, download it, and then execute again. We've got an error here, the lemmatizer is not defined. So it's talking about this line. That is the lemmatizer instance. This one in here. So I'm going to get that code and just place it in here. Execute. So that's the lemmami function, that's the lemmatizer. Now we go down and execute that again. We need the WordNet library as well, so I'm going to convert that in here. So I'll execute that in here as well. Execute that again. If you want to see what TF is, you can just call it. So it's a matrix 3 by 8. Now I know you are completely lost at this point, so I want to show you what this looks like actually. So this is an optional step, this code cell here. To see this matrix, you can do tf.toArray. That is a method that will display the actual matrix. This looks intimidating, but I'll explain you what it means now. So this is a matrix made of lists. We have one list here, so it starts in here and it ends in here. That is the first list. Then we have the second list, it starts in here, it ends in here, and then we have the third list. So we have one list for each sentence, because you see that this TF was built from the sentence tokens variable, which is this one in here. So it's a list of 3 items. Now, let me copy that list and just put it in here temporarily just to see what's happening here. So one sentence, one list. And then if you look inside each list, you'll see that we have 1, 2, 3, 4, 5, 6, 7, 8 items. 8 numbers. The second list also has 8 numbers if you count, and the third one as well. So each of the lists have 8 items. Why 8? Well, that is because the longest sentence in our text has 8 words. We can count 1, 2, 3, 4, 5. This is not counted, these articles. So 6, 7, 8 words, and each number represents the weight of each word in the entire text. So for example, 0.3 means the weight of originally in the text is that number. And then we have vegetables, 0.52. It has a bigger weight because it's being used here as well and here. To get a better representation of this matrix, you could use pandas, import pandas, and then create a data frame from pandas.dataframe. So again, this cell here and that one are optional. They are just to show you what's going on in here. And then you say tf.toArray as a source of the data frame. The columns will be TV, so the vectorizer, which we defined in here. dot get feature names method. So call that method and then print out df in here. So that is a better representation. You see the weight of the word B is 0.3 and the weight of collect is 0.52 in the first sentence, and then the weight of those words in the second sentence, and so on. For example, the weight of originally in the first sentence is 0.52, but the weight of that word in the second and third sentences is 0 because there's no such words in those sentences. That is why we have all these zeros in here and also here, so it's the same matrix. Alright, so this is how it works, but we need now to add another sentence to the sentence tokens. So when we created the sentence tokens, we use the text variable. We need to also append the question variable in that list of sentences. The question variable is this one, which has this question. So execute that. Now you see that sentence tokens is this list, and then you execute all the other cells to redefine them with that question added, all of them. You see the array now has 4 lists instead of just 3, and we delete that. And we also see the data frame has 1 more row at the end. And now to find the similarity, finally, let's say values are equal to cosine similarity, which we need to import from sklearn.metrics.pairwise import cosine similarity. So cosine similarity now finds the similarity between two matrices. The first one being TF minus 1. So TF, you know TF is this. And TF minus 1 is the last item of that matrix. So the list that represents the question. So we want to compare that question to the entire matrix. TF minus 1 with TF. Execute that, and this is what we get. We get an array, and this array now has 4 values, as you see. Each value represents the similarity between the question and each of the sentences in the text. So that means how similar is our question, what are vegetables, with the first sentence. So the first sentence is, let me get this just to keep it here for explaining you what's going on. So what are vegetables is similar with the first sentence at this coefficient 0.39, and then it's similar to the second sentence, which is vegetables are plants. It's 0.59 the similarity coefficient for that, 0.46 for the other one, and then we have this 1. 1 is the similarity between the question, what are vegetables, and the same question, what are vegetables, because you know we appended that question to the sentence tokens. So the similarity between two identical sentences is 1. It's 100%. Now, we want to find out which sentence is the one that has the maximum value in this list. So let's find that out. We need to extract the index of that sentence. We do that using values.arg sort. You call that method, And if you see what index is, now you'll get an array, but you only want the first list because we have nested lists here. So we get the first list, we execute again. You see, now there's no two lists, but it's only one inside. And then out of that first list, we get the -2 index. So that will give us the index of the maximum value. Actually, it's not the highest value, it's the second greatest value, because the first one is 1. So if we applied -1 here to get the last value out of that sorted values, we get an index of 3. So that's the index for that, but with -2 we get 1. So index 0, index 1, we get the correct index for that maximum value. So that's a variable we need now in just a bit. However, first we want to point to values flat. So we want to say values.flatten, and we get this. So it's the same values basically, but we don't have these two nested lists, we have only one list in here. Lastly, now we can extract the coefficient, which is equal to the values flat matrix -2. So we want to get always the before last item. So now we have the coefficient, and we could say something like, finally, if coefficient is greater than, well, let's put a threshold of 0.3, then we return, or we print out whatever we want to do. We print out from sentence tokens, we print out the item with index 1. If you execute that, you get the answer of that question. So the question was, what are vegetables? And the answer is, vegetables are all plants. So that is how you can get the most similar answer given a question from a piece of text using this quite advanced algorithm that you saw in here. So thank you for following this, and I'll talk to you in the next videos. See you. In this video, you learn how to do sentiment analysis with Python. Sentiment analysis, in other words, is finding the mood of a piece of text. So if it is positive or negative. Let's suppose you want to analyze a Twitter tweet or a Facebook post. So you can write a program which tells you if that text has a positive attitude or a negative attitude. And this is known as sentiment analysis. We're going to work on a Jupyter notebook. I am specifically on DeepNote here, deepnote.com. And we're going to use NLTK for this. I'm going to use NLTK because NLTK has a database which is pre-trained, so it has all the words and it knows the mood of each word. And that is known as the Vodder lexicon database. So first you need to download that database using nltk.download. If you're curious, Vodder means Valence Aware Dictionary and Sentiment Reasoner. So that is the dataset that you need to download. So execute that cell and then create another code cell. And I'm going to use a variable here and then use a class which you need to import from nltk.sentiment. Import sentiment intensity analyzer. So that is a class that handles all these analyses. So you want to instantiate that class. So once you execute that cell, then we have access to that class in this session. So I'm going to create an instance of that, store it in the analyzer variable, and then I'm ready to find the mood of a text. For example, let's say text1 is equal to, hey, what a beautiful day. How amazing it is. So that is the text we want to analyze now. And to do that, you want to point to analyzer dot polarity scores. Polarity scores will calculate the positivity score and also the negativity coefficient. So positivity coefficient and negativity coefficient, or scores if you want to call it like that. Inside this goes the text you want to analyze, text1 in this case, and execute. I've got an error, analyzer is not defined, I forgot to execute the analyzer definition and the text as well. So there we go. The output of this is a dictionary. So let's see what this dictionary is made of. It has this pair of key and value, another pair of key and value, a third one, and a fourth one. The first one shows the negativity coefficient, and in this sentence it's 0, so there's no negativity in that sentence. The neutrality coefficient is 0.42, so the analyzer judges that this sentence is that percentage of neutrality, and actually the sum of these three coefficients is always equal to 1. So in this case, 0.0 plus 0.42 plus 0.58 is equal to 1. So if the coefficient of positivity was less, then we would have more in here or more in there, so that we end up with 1 in total. So as you can see, this sentence is more positive than neutral, and more positive, of course, than negative. And then we have this compound. Compound can range from -1 to 1. And the closer it is to 1, the more positive the text is. So that is another way to judge the positivity of a text. You can basically create a conditional now, such as if the value of compound, so I'm accessing the value of the compound key here, so that it will be equal to that coefficient of the compound. So if that coefficient is greater than 0, then we print out positive text, else print out negative text. And then we're going to get positive text, since compound was greater than 0. If you want to go further and practice this, you can use the Twitter samples, which are available from NLTK, so you need to download them using Twitter samples here. So execute that. Oh, fix the typo, download. There we go. Then down here, you can access Twitter samples using nltk.corpus.twitter samples. So the dataset we have just downloaded, .strings. This method will give us a big list of tweets. So there's a lot of them. You can check the length of this, and we see the total number of tweets in this list. So that is a list of strings. We have 30,000 tweets in here. So if you want to extract a single tweet, so tweet 1, for example, is equal to that, and just get, for example, the tweet at position 42, and that will give us one single tweet. So that is a tweet, and you can analyze these tweets now using the same analyzer. So analyzer dot polarity scores, and here goes the tweet 1 in this case. And then we see that the negativity is 0.2 here, neutrality is 0.56, and positivity is a bit higher than negativity. So the compound coefficient is more towards positivity. Let's try another one. 1045. So you can go up to 30,000. And this should be quite negative, I expect. So let's try. Yeah, so the compound coefficient is minus 0.8, obviously. And that is how you can analyze the moods of texts, and this can have many applications. So I just gave you an example, a general example, but you can do different things, like you can even analyze audio. In the course you have a lecture on speech recognition, so you can convert the audio to text and then find the moods of that text. So technically you're finding the mood of the speech in the audio. That's one more example, but it's up to you what you can do with this analyzer. So I hope this works for you, I hope you like it, and I'll talk to you later. See you.